Welcome to Monochemistry. In this lesson, we're going to look a little bit at a concept called activation energy, and we're going to also look at how temperature affects the overall rate constant of a reaction. Before we do that, we're going to review a little bit here. There's a theory out there that you've heard of, I hope, because we've talked about it, called collision theory, and that theory essentially just states that molecules, in order to react, must collide. And so I just have a picture here of some molecules colliding. Okay? Unfortunately, collision theory leaves a couple of very important things out. We'll talk about that on the next slide. Let's say we have a reaction occurring between molecule A and molecule B. Collision theory essentially states that every time they collide, they're going to turn into products C and D. But in reality, that's not going to happen. A and B are not always going to hit each other in the right way, nor are they always going to have enough energy for a reaction to actually occur. Because remember, sometimes molecules, when they collide, bonds have to be broken and new bonds have to form. There has to be a certain amount of energy for that to happen. So collision theory is a little short. We have to advance then to the kinetic molecular theory, which, as you folks know, states the three important things. First of all, they have to collide. We already knew that. They have to collide, but they also have to collide with enough energy and in the proper orientation in order for a reaction to occur. That barrier that they have to overcome is called the energy of activation. Molecules will only react if they overcome that barrier or that energy of activation. Now, energy of activation, according to your textbook, is the minimum amount of energy required to initiate a chemical reaction. And the symbol they use for energy of activation is this, E subscript A. Now let's get back to our discussion. We know from the discussions we've had on kinetic molecular theory that there are basically four ways in which one can alter the speed of a chemical reaction, or in other words, change the chances of molecules colliding, increase or decrease the chances of molecules colliding. Changing the temperature is one, increasing the surface area is another, changing the concentration is another, and whether or not a catalyst is present is the last one. Those are the four things we discussed. But let's go back to reaction rates, because that's what we're talking about here. So this rate constant here that we have written out for this reaction, and obviously this is both first order because I didn't write anything in, so overall it's a second order reaction. Anyway, the rate constant itself is dependent on the temperature. If the temperature changes, the rate constant changes. Okay, so let's just look at this logically. The higher the temperature, the more likely collisions are to occur, and the more energy the collisions have when they actually do occur. That's going to increase the rate of a chemical reaction, which in turn is going to affect the constant, right? The lower the temperature is, the slower the reaction goes, which of course again is going to affect the rate constant. It's all a matter of collisions. Okay, so temperature affects the rate constant, or if you prefer, the rate constant itself depends on the temperature. I'd like to talk a little bit more about activation energy. I'd like you to copy, there's two graphs. This is the first one. This is an endothermic reaction. We'll talk about what that means in a second. You should draw this. But we're going to talk about activation energy and activated complexes. Okay? So let's say we have our reactants again, A plus B. And over here we have our products, C plus D. Okay? In order for this reaction to occur, we talked about they have to collide. But not only that, they have to collide with enough energy to overcome this barrier right here. There has to be a lot of energy gained by those two things, and they have to collide with that energy in order for a reaction to occur. So the distance between the top of the hump here and where the reactants start off, what energy level they start off at, that's the activation energy. Okay, let's just go back to this graph. First of all, this is a measure of the energy. This is the reaction coordinate. It's kind of like time. right? It's how far along the reaction has progressed. It's not really a measurement of time, but you can kind of think of it that way just for our intents and purposes here. Okay, so this is the energy of activation, the EA. This is the minimum amount of energy required to make this reaction happen. Now, up here, during this part, we have our transition state, or our activated complex. A and B are going to collide. They're going to stick together somehow, and they're going to form these new products. So up here we have our transition state, or if you prefer, our activated complex. They're going to collide. They're going to hit each other. Bonds are going to break. New bonds are going to form, and then eventually they're going to turn into C and D. Now, just one other thing I want you to note on this graph. Notice that the energy level of the reactants is lower than the energy level of the products. Overall, this reaction then is going to have a positive delta H. In other words, it's an endothermic reaction. You had to add energy to it in order to make it happen. And that's how you tell. The energy of the reactants is lower than the energy of the products. Make sure you draw this graph. You can label some of the things. You don't have to have all these circles like I have here and here, but you label some of these things so you know what they are. Okay, this is the other type of graph. This is an exothermic. Notice that the energy of the reactants up here is much higher than the energy of the products. Okay, again, in an exothermic reaction, you require the energy of activation. And of course, there would also be, in the transition state, an activated complex. It's kind of an intermediate between these two things. It's not called an intermediate, but it's an intermediate state, a transition state. It's the transition between the A plus B and the C plus D, where they collide with enough energy. Okay? That's an exothermic one. How you tell is that the energy of the reactants is much higher than the energy of the products, indicating that energy has been released to the surroundings, or a negative delta H. Now, in terms of the textbook, it goes through and it talks about an equation called the Arrhenius equation. Now, that is an equation that you can use to calculate the energy of activation given a specific reaction. And that's important. Think about this. If you're a scientist, you're working in a lab, you're working in an industry, and you need to know how much energy it's going to take for this reaction to happen. It helps you figure out where you need to store things. It helps you figure out how much energy is going to be required to actually make a reaction happen on a mass production scale. And if you can calculate the energy of activation, and more importantly, if you can figure out ways to lower it or change it, manipulate it, then you're going to be able to save companies lots of money, but also you're not going to cause any industrial accidents. You're not going to allow things to explode. They're going to be stored in safe places. Okay, so this type of thing, this type of equation, this type of work is done by scientists the world over who work in situations where they are worried about reactions occurring between the chemicals that they're storing, or just reactions happening in something that they're producing. Okay, make sure you bring any questions you have to class. The Arrhenius equation itself, although it's in your textbook, is not technically in the data booklet, so we're not going to specifically go over it, but I would suggest that you try the example problem in this section on page 586, just to make sure that you can actually manipulate that equation. It's not a hard equation to use, but you should try it anyway. That in a nutshell is activation energy and how temperature or reaction rates are dependent on temperature.